Data protection and local availability are key requirements for IT managers. This video demo shows how ECS can efficiently meet those requirements when federating VDCs that are dispersed in multiple sites. Let's start by discussing traditional data storage protection and defining some of its characteristics. First, it's a general practice in the storage industry to protect production data by keeping a second copy of that data in an off-site location. This doubles the storage cost factor, also known as 2 times protection. This solution might be sufficient for a situation involving 2 sites, but what if the scenario involves 3 sites? One solution could be to mirror copies in sequence from one site to another. This approach still implies that twice as much storage capacity is required. This may be enough for protection, but is it sufficient for user data access? Users can't easily collaborate or share data to work on projects. One solution could be to reverse the situation so that copies go both ways. In this case, the requirement to store a secondary copy off-site is fulfilled. But your data now has 3 times protection. This is what happens when you choose to replicate to all sites within ECS configuration. Because each site has a full copy of each remote site, all users can access all data. One way to solve the issues faced in the previous scenarios is to divide each of the duplicate copies in half and send 1/2 to each remote site. That way, if a site is lost, the remaining 2 sites can work together to support the missing one. This solution meets the off-site and 2 times protection requirements. But it can't provide users with easy access to all data. One way to fulfill our 3 requirements is to take a full copy from each of the other 2 sites and perform a mathematical computation to merge them into a single copy. Such a computation using a simple XOR operation enables a site to have a consolidated copy of the data from the 2 other sites. In this scenario, if a site becomes unavailable, the 2 remaining sites always have the sibling parity of the missing one, enabling them to reconstruct the data. This solution meets both the off-site copy and 2 times protection requirements, but also allows universal access to data. In the event of a site failing when you are protected by XOR optimization, ECS can reconstruct data from a missing site. Consider that Site 1 goes offline. A request for data from Site 1 comes in to Site 2. Site 2 has the parity of Sites 1 and 3. By requesting Site 3 data and combining it with a local parity data, Site 1 data is easily regenerated. In order to benefit from the XOR optimization, you must meet some replication group requirements. First, the replication group must contain a minimum of 3 sites. Second, sites with XOR protection must contain replica copies from all other sites in the replication group. Finally, you must disable the replication group option, Replicate to all sites. Let's walk through some multi-VDC data protection scenarios that span 4 sites. The starting point is where the primary copy of chunk A is on VDC 1, chunk B is on VDC 2, and chunk C is on VDC 3. All 3 chunks are replicated to VDC 4. The VDC 4 chunk manager table is updated to reflect the primary and secondary data location and specify the type as copy for all 3 chunks. Because all chunks are of the same size, this will result in a total of 768 megabytes of chunk space being used to store 384 megabytes of objects. Because VDC4 has a type of copy for chunks from all other VDCs in the replication group, it can perform an XOR operation of replicated chunks A, B, and C to create a new chunk, D. The VDC4 chunk manager table adds information about chunk D after XOR encoding is complete. The secondary copies of chunks A, B, and C can be removed from VDC4 so that space can be reclaimed. Thus, rather than using 384 megabytes of chunk space in VDC4, ECS now only uses 128 megabytes of chunk space. Also, the VDC4 chunk manager table updates the type of chunks A, B, and C to encoded. In the event that VDC1 goes down, VDC4 can reconstruct chunk A by using chunk B from VDC2 and chunk C from VDC3, and then perform an XOR operation on them with chunk D from VDC4. Similarly, if VDC2 or VDC3 goes down, VDC4 can reconstruct the respective chunk by using the sibling VDC primary copies of the chunk and performing an XOR operation with chunk D from VDC4. Now chunk E is written to VDC1 and replicated to VDC3, and chunk F is written to VDC4 and also replicated to VDC3. The VDC3 chunk manager table shows that chunks E and F are of the type copy. However, VDC3 will not perform an XOR operation until it receives a chunk from VDC2. Chunk S, T, and U are written to 3 different VDCs and are all replicated to VDC2. Because VDC2 has a chunk from all other VDCs in the replication group, it can perform an XOR operation on these chunks and create chunk V. VDC2 can then remove the replicated copies of chunks S, T, and U and update its chunk manager table accordingly. As the number of VDCs in a replication group increases, the ECS algorithm more efficiently reduces the protected data overhead. The charts shown here provide information on the data protection overhead factor based on the number of VDCs in a replication group for the normal erasure coding scheme of 12 plus 4 and the cold archive erasure coding scheme of 10 plus 2. The charts also illustrate how ECS becomes more storage efficient as more VDCs are added to the replication group. Please note that this data protection efficiency is only achieved when the same amount of data is written on each VDC. Also note that storage efficiency for the case of a single VDC is only due to erasure coding, that is, the local protection, and only where there is no multi-VDC protection.